Okay, so let us start. Today what we will discuss is chapter 7. Okay, it's about data modeling. So first, let's take a look about the uh, idea about modeling. Okay. Uh, so for the modeling, it's we use the data. So in the previous chapter, we already learned how to handle data. And after you do data cleaning, and sometimes you may also need to do data wrangling. And then you can do modeling. Okay. So modeling is to use a math or statistical models and also machine learning models to represent the data distribution. And previously, if you recall, when we discuss the data analysis with the various plotting, it also reviews some data distribution. But here, it's going to use some model to represent data distribution. Okay, and because you have model created, then for the new data for the new data point, then you can also make a prediction. Okay, so that's the major one of the major goal for the modeling. Okay, is you train the model and then you do the prediction. You see, that's just like for the Chat GPT, why it uh, uh, can do so many things, right? Now it's including coding, as it's because it's trained on the uh, previous available data using model to train, is it? So that's why when you give ChatGPT a question, it's your question. So it's based on the trained model, then it give you the prediction. Okay. So that's the general idea. And for the modeling, it can also help us understand the past events. And this belongs to, we call it descriptive analytics. Okay. And also understand why the events occurred. So we call that diagnostic analytics, and also predict future occurrence. So that's belong to predictive analytics. Okay. And generally speaking, for the modeling, using Python-based library, over here, we are going to discuss a statistical model and a machine learning model. Okay. For the Python-based library and packages, it include, so we will also see that the statistical models and the scikit-learn. Okay. Statistical model is for the statistical modeling. Okay. So it includes a quite a broad range of traditional statistical tools. And so we are going to cover just some basic introductory level, okay, so that you have some idea. And the other one is for machine learning. So this is a classic one. Scikit-learn, if you recall previously when we discussed data cleaning, wrangling, and aggregation, we also touched scikit-learn package. And over there, we use it to pre-processing package, sub-package, okay. So we are going to learn scikit-learn. And for TensorFlow and PyTorch, they are quite powerful in handling the complex model using deep learning. Okay, so we are not going to cover TensorFlow and PyTorch because they belong to uh, they more focused on machine learning and deep learning. Okay, so we are going to touch also some very introductory level of scikit-learn. Okay, so that's the general idea about modeling here. And the first model we are going to learn is about linear regression. So I believe everyone is quite familiar, okay, with the linear regression concept. So what is linear regression? So keep this in mind. It's for continuous value modeling, okay, continuous. And there is another, it's for discrete value, okay. And later on, we will also see like discrete value, and it's involved like so linear regression is for continuous and also involved with value, continuous value, like estimation, or you call it a prediction. Okay. So continuous value. So it's to try to find a linear equation, or we say linear relationship between an independent variable x and the dependent variable y. So try to find the best fit linear relationship between independent variable and dependent variable. Okay, and it's represent continuous value estimation. There is another kind, it's discrete, and we call it like a classification. Okay, and we are going to learn that in the second model. Okay, so linear regression is to find the linear equation that's best to fit the data points. So those data points are the known data points. And once you build that linear equation, so generally you can write like this, like y equals alpha plus beta x, if you only have single independent variable. So it can be represented like this relationship. So so you try to find a linear equation like this, and that best fits your data points. And all of the data points are the known data points. And because once you know this relationship, and then when you have a new data point, and for the new data point, maybe you only know its independent variable, x. Then using this model, you can predict the y value. Okay, so that's the idea. So best fit independent dependent variable with linear equation that's going to minimize the overall prediction error. Okay, so that's the goal. And so single independent variable can be represented like this. And if you have multiple, then you can represent like alpha plus beta 1 x1 plus beta 2 x2 and plus like beta n xn. Okay, so then that's you have n number of independent variable. Okay, but the relationship is still linear. Then the goal is to find the best, we call it coefficients. Okay, that's going to minimize the overall prediction error. Okay. So this is regarding the concept, very basic general concept about linear regression. Okay, then next, let's see. So how do we find the best fit model, etc. In linear regression? So in statistics, they use a concept called OLS, so ordinary least squares. Okay, so the idea is, so here you have the model. So this is the model. And within the model, alpha and beta, those two are the coefficient. But you don't know, it's unknown. And so like in this diagram, so in this diagram of the blue dots, they are actual data. Okay, for actual data, so you have like, for suppose like, let me change the color, okay. Suppose this data points is called the eyes points, data point. Okay, eyes data point, this one. Okay, then it has a value xi and also has a value yi. Okay, and xi and yi both are known. So basically, they are sample point. It's a sample data point. So their x value and y value are known. Okay, so we have, assuming total you have m samples. So each of it you have like xi and yi. Okay, so you have m samples. Okay, so the estimation. So this is the linear model you try to find. Linear model. You try to find, okay. So it can be like this green light, can also be this green line, can maybe also this green. So it can be, so the coefficient can be any value, is it? So it can be any value, the horizontal, it can be any value. So then among all of those, which one is the best? That will make all of the samples like close to this red line. Why we choose this red line, is it? Yeah, so here is the idea why we choose it. So we use a concept called the ordinary least squares. Okay, so we can represent the line. So the value on this is called y estimate, or a lot of time we call it y hat. Okay, so predicted. The predicted on, so based on the linear regression line, okay? And so once we figure out alpha and the beta, okay, if you have the x value, then you will have using this model to figure out this predicted value, okay? So like in this case, okay, so this is that xi and yi. Okay, And so we can find the difference. Is it so? This is xi. And with this xi and this point on the red line, then this is y I hat. Okay, so that's the predicted, is it? So the difference between this y hat and yi and yi. Okay, and then for all of those points, and we square that. Okay, so we have m samples. So you try to minimize this. Is it if you can find the best that minimize all of the difference and we square it, is it? Then we say, okay, this line is the regression line. That's the best fit one, regression line. Okay. And to find the minimize, basically this y hat can be represented. So basically then it's changed to the ish problem of alpha plus beta xi minus this yi. Okay, and in this equation, alpha and beta are unknown. If you try to minimize it, then you can take a derivative of this expression. And then make it equal to 0, is it? Then we can figure out what alpha is and what beta is. So that's the way we find out alpha and beta expression. Okay, so this concept is called ordinary least square. Okay, so the objective is that the least square is find the value of alpha and beta that minimize the sum of the square difference between y and ye. Okay, it's just what I just explained. So visually, we can also understand, is it like this? Because if you use other slope and other intercept the line that so this summation of the square, it's going to be larger than this one. Okay. So this one is a least square one. Okay, so we call it ordinary least square. Okay, so that's a linear regression. Okay, the idea, and then we will see. Okay, we use statistics model, and we can also use a machine learning model. And so we are going to take a look at our code. Okay, so the model we are going to use the data. It's regarding that auto. Okay, and it's a pretty simple one. And here it gave us the glimpse of the first 5 data. Okay, so we only have one independent variable x. And we also have the y values, okay? And here it also gives us a description about this data. So total we have 63. So m, the number of samples is 63. Okay, and it also give us some other statistic descriptive data. Okay, then first, let's see. So how do we do the linear regression? Okay, so first we use the model from the statistics model. Okay, and if you want to use, you call the API model. Okay, and from the first one we are going to use is we are going to use formula based. We use a formula-based ordinary least square. Okay, so you import the ordinary least square model. Okay, and if we use formula-based, then over here you need to provide the formula in text because it's regarding linear regression. Okay, so it knows the independent variable and dependent variable and where the data set is, and then you call the fit, okay, to get your model, basically to find the alpha and the beta, okay. So after that, you can analyze if the model fits or not. And here we choose the ANOVA model, ANOVA analysis. So analysis of variance. So we choose analysis of variance to overall estimate the model's fit or not. Okay. And so the result is given here. Okay. So in this, so this is the analysis of variance ANOVA's reports. Okay, so ANOVA's report is one way ANOVA reports when it used for linear regression. For linear regression, so it will give you the idea about overall model's fitness. Okay, so here's the result. So regarding the independent variable, so this is degree of freedom. Freedom, okay. And because we only have one independent variable, so that's why it is 1, okay. And the residual is 61. So its total sample is 63. So we have 1 from X. We also have another one. So this is for the constant term. So basically it's that intercept. Okay. So that's why we have 61 for the residual. Okay. So that's regarding degree of freedom report. And this column is regarding sum of square. Okay, so previously we explained this is ordinary list of square, is it? So sum of square. So one is for X, one is for residual. Okay, so what are those? And here we also have mean square. Okay, and then we also have F statistic, and here we have the p-value for the F statistic. Okay, so let's take a look. The sum of square regarding X and the residual and the mean and the F statistic. Okay, so here anyway to give you the overall idea about your model's fitness. Okay. And using those variance, so focus on variance. So let's see the sum of square for x. The other one is for residual. Okay. So the sum of square for x is measure the predicted, so y hat. So this is y hat, the variance and the mean. Okay. So the mean is you have the samples, m number of samples, and you add all of the y values, so you will find the mean. So that's the difference between the predicted and the mean. Because the predicted you have so I from 1 to n, you have m number. Okay, so this is a square or sum of square for x. Okay. And the other one is sum of square for residual. So residual is measure observed value y from difference from the predicted. Okay, so it is so yi, the difference between, so this is observed with the predicted, and you square it. Okay. So one is for the difference between predicted versus the mean. The other is difference between observed and the predicted. Okay. And then the mean is just divide each one's degree of freedom. Okay. So for the x one, then it's divide by the degree of freedom for the independent variable. And the mean then is divided by the degree for the residual. Okay. And then F status. F status, so it's mean for x over, so divide by mean for the residual. Okay. So then let's see. Okay. If you recall this, so here, if you recall the idea, so here is the points, is it, and here you have the line. So this is a predicted line, and this is observed. So that's regarding the sum of the square. So then you just think about, is it this value, the less the better? Is it this value? So we try to minimize it. So the less, the better. Okay. And then how about this? This is regarding the difference between the observed. So this is the average. So it's a horizontal line. So the difference between this, is it? So basically what we want, so when we think about linear regression, we want the slope. You have some slope, not a zero, not the no slope. So versus the no slope. So if no slope, so that's basically the mean of y, is it? So you want this be larger. The larger, the better. Is it? This is the lesser, the better. Is it? So then for the F status, based on the relationships, this one divide by this one, is it? So then that means for F statistic, so the larger, the better. Okay, so that's regarding F statistic. And then the other one is the p-value. Okay, so the p-value, and generally, if the value is a small one, typically if it's less than 5%, then that indicates strong evidence. Okay, so there is, so basically there is linear regression. Okay, so over here we explained, so using the different variances. That's why this is the ANOVA. Okay, analysis of variance. Okay, and it focus on variance. Okay, so for the F statistic, so it's focused on variance analysis. Okay. Now we can see the using statistics model, the Python package itself is pretty straightforward, okay, and easy to use, okay. And it's also generate a very detailed report. So we can see it's quite nice, okay, regarding this. So this is, we use formula based. And what next one, let's take a look. And this time, we use array-based. So we still use the statistical model, okay? Use the ordinary least square, but this time it's array-based. We don't need to provide the formula, okay? And this time, then in this case, you also need to manually add that intercept, the constant for the independent variable, okay? So you call the add constant, okay? And then you plug in that independent variable and dependent variable. Then you call the fit, okay? And after that, you call predict. So you call predict, so basically you can find off the y-hat values, okay? And for this model, you can also directly have the summarized result. So you call the summary, okay? And it also give you the R squared value, okay? And here, from we can also find the mean squared error, okay? And the basically this is R score, okay? But this mean squared error, it comes from scikit-learn. So it's some performance measure metrics, okay? So you can also use the mean squared error. So you can, so here the idea is just, you can measure the performance using different metrics. So let's see the result. Okay. And first, let's take a look. So this is that summary. So you can see the summary gives you the quite detailed report. Okay. So it tells you, what is dependent variable and your model, as it is ordinary least square. It also tells you the total number of sample and the degree of residual, degree of the model, okay? And here is that R squared, and we will see what is R squared. And here's the R adjusted R squared, okay? And F statistic previously we already explained, okay? So this is the p-value for the F statistic. And p-value is an important metrics that you can use to measure if the model fits or not. And so this value should be small, okay? The smaller, the better. But if you just use a p-value, a lot of times it's not enough, okay? But clearly from this number, we can see this is very, very small, okay? It's 2 to the power to negative 25, quite small, okay? And the log likelihood, AIC and BIC, they are also used to help identify to report about the models, okay, and we will see. And then over here, it also give us the coefficient. So you can get, so this basically is beta and this is alpha, okay? Intercept and slope. And the slope. Okay, it also gave their standard error and t statistic and p-value for t statistics. And this is 95% confidence interval. So you see, it report quite information for us. And it has another section. And plus more, okay? So all of those are more statistic related regarding the metrics, okay? So we can take a look some of the important ones in our case, okay? And the R square, if you remember, or the R2 score, okay, it ranges from 0 to 1. And generally speaking, so if it's close to 1, then that means the model fits. Model fits, okay. So that's if you use R square to measure, okay. Why just explain that it means the independent variable X predict the dependent variable Y quite well. Okay. So what is R squared? R squared is 1 minus the ratio between two squares. So what are those two? The first is the sum of square of error, or we call it residual. Residual is what is the difference between the actual value, so yi, and the predicted, so yi hat, and the square. So I from 1 to m. So this is sum of square of error, okay? And previously we also saw it's sum of square of x, or no, of residual. Okay? And we want this value be smaller. The smaller, the better. The smaller means the difference between these two. So kind of close. Is it the overall summation of the square of error is smaller? Okay, and that's why we call it ordinary least. So this is least square. Okay. And the other one is total sum of squares. Total sums of squares between actual and the mean, okay? So yi and y, that mean value, okay? And then you square it, okay? And if you recall, the idea is you want your linear regression, the slope. You don't want slope is 0, is it? Because this is a horizontal. This basically is a horizontal line. Okay, so the slope basically is 0. Is it? You don't want slope to be the average. So if the slope is larger, normally it's better. Is it? So you want this to be larger. Is it? So this larger, this smaller, so that means this is smaller. Smaller, that's why R squared is close to 1. Okay, that's why. Then that means it's the model fits well. Okay. So that's why here it says higher R squared value predicts better fit. Okay. But here there's some notes. Okay, uh, it said R squared doesn't tell if the coefficient are statistically significant. It doesn't tell us. Okay. And also, if R square is small, you can increase simply, it says, by adding more independent variable to the model. Okay. But sometimes that's not a good solution, because if you have more independent variable to your model, maybe your R square value is large, okay, and you think your model fits well, but when you have a new unknown value, a new sample coming in, and you want to predict the Y value, then it may be off a lot. That concept, we call it overfitting. So it can cause overfitting with this. Okay, so so that's why it's preferred to use adjusted R square value. Okay. Well, that's why over here it says we use adjusted R square value. So adjusted R square, where it can penalize the model for including unnecessary predictors. So those unnecessary predictors, you add more independent variable. Okay. So these two are kind of related. Okay. So adjusted is as always less or equal than R squared. Okay. So prefer you use adjusted R square to measure. And also a higher adjusted R square is better. And also it's very useful when you compare different models. Okay. Because this is already adjusted. Okay. It use some approach to penalize the model to include unnecessary, to try to prevent overfitting. Overfitting, okay. And in machine learning, we'll discuss overfitting. So various approaches to prevent overfitting a lot. Okay. So over here, you can see in statistics, we also discuss the overfitting concept. And if you recall, there are some other measure statistic. Okay, the log likelihood. What it does, it's to how likely to observe the data, you see, given the model's parameter. Okay, because we already know alpha and beta values, is it? So then it can give you some idea how likely you can observe the data. Okay. And AIC is a key information criteria. Okay. This is as its criteria for model selection. Okay. It can balance the goodness of fit of the model with its complexity. So it's also kind of tried to find the trade-off, okay, between um, the performance and your model's complexity. Because if model is more complex, so model more complex, definitely the performance metrics is better. but that may cause the issue of overfitting. Overfitting. Okay, simple model won't have overfitting. Okay, so you need to find the balance, a good fit between these two. Okay, so here it says that the AIC can achieve, can do this kind of balance. So BIC, Bayesian information criteria, it's also try to balance the fit and the complexity. So this is kind of like in machine learning, we also use some approach. We call it like a regularization to prevent overfitting. And sometimes we also use reduction of dimensionality. But those normally is machine learning model, machine learning. Okay. So this is regarding statistic model is different. So they approach the same question that from different angle. And statistics is more based on math and the statistic formula model. Okay, machine learning is different. It's use gradient descent generally. Okay, and then now we come to a machine learning model. Okay. Oh no, this is still that statistic, but use array based. Okay. Yeah, we just explained about its report. And what next one try to do is we do some plotting, okay, use matplotlib and cbound, okay. And over here, we also try to find the 95% or the upper and the lower confidence interval. Okay, and then we do some plotting, okay, with the regression line, linear regression line, and versus the observed data points, so that we have some visual understanding about the linear regression and if the model fits or not. Okay. So to get the confidence uh, interval, the lower and the upper one, here we use this model. We use weighted least square. And over here, the idea is for the each observed samples, they also add weights to each sample, to each data point. Okay. And anyway, so using this model, it will directly give you the confidence interval. Okay. With this confidence interval, then we can do plotting. So let's kind of review, okay, chapter 5, what we learned about plotting. So here you do the subplots. So we will have two subplots, okay, in one row, okay. So on the first plot, we are going to plot what? Plot the sample points, okay, in blue color. Then we are also going to plot, what is this? This is the regression line, okay. So independent versus the predicted value, okay. Then the title, label, legend, And over here, what we plot is the confidence interval, okay? And using their respective X value. So this is the first plot. And then for the second plot, and we use C-bar. If you recall that C-bar directly can plot the regression line, okay? So if you provide the data set and specify the independent dependent variable, okay, it will directly generate and as well as confidence interval, okay? So C-bar, yeah, C-bar is, then we don't need to manually do the calculation. Then can give you some idea. So here we have this comparison, okay? So this is the confidence interval that we use that weighted least square to find the upper and the lower bounds, okay? And this is the regression line, and here are the sample points. And from this plotting, we can see this model fits quite well, okay? And the majority of the samples also fall within the confidence interval, okay? And over here to also give us the C-bar, also give us the linear regression so plotting. Okay, and then now we move to the linear regression using machine learning. So from machine learning's perspective regarding linear regression model, okay, and to do it, you need to import this linear regression model, okay, and here you get their NumPy array from the data frame, okay, pandas data frame. So you create the model and then you plug in the X and Y values. So, and in machine learning, it's not called X, Y value, okay? So X, so for independent variable, normally we call them features. And Y, we call it outputs or targets. And if you recall, previous we learned the feature scaling, is it? Yeah, so that's why we call it features, okay? So then you fit the model. After you fit, then you can predict the value, is it? And with machine learning's model linear regression, then you can directly get its intercept and coefficient values. And to measure the performance, you can call that R2 score and mean squared error. Okay, we already, so this R2 score basically is that R squared. And this mean squared error is regarding Y and the predicted, okay, square, but you also find the mean, okay. So that's why we call mean squared error, okay. And if you recall R squared, if it's getting close to 1, then it's better because the value is between 0 and 1, okay? And after that, we can also plot the regression and also use C-bound to do comparison. And here is the machine learning's result, okay? And so this is from the classic. This is from classic scikit-learn linear regression model, linear models, linear regression. Okay, and you can also use a neural network to do that. So let's see. Okay, so scikit-learn, it also provides the neural network. Okay, and for linear regression, then you can use the multiple layer perceptron neural network. Okay, uh, we can try this to see how it performs. Okay, so you use this model, and here you define the number of hidden layers. And over here, we just take the default. And here it uses specify the maximum number of iterations. Okay, because in machine learning, we don't directly use math to derive alpha and beta. And in machine learning, we don't call it alpha and beta. In machine learning, we call them weights. Okay, so basically, you use like for our case, we just have one independent variable, and then it's so for each independent variable, you use a weight to time it, and this is we call it a bias term. Okay, and then you use this as your a model. Okay, so in machine learning, then the weights are unknown. So similar, okay, the weights are unknown. So your goal is to find the optimal weights that can best predict your model. Okay, so there are some similarities between the concept of machine learning prediction and the statistic, but the way to arrive the unknown weights is different. Okay, so in statistic, you go with the mathematics derivation to find alpha and beta. So alpha beta does have the formula to represent it. And in machine learning, it's different. To find W0, find the weights, we use a method, we call it gradient descent. Gradient descent. So it's kind of you train, okay? And then to find the lowest point with the weight curve, then using that as your weights. So that's why over here it involves iterations. And if your gradient descent cannot converge, basically, then that's why here we set the maximum number of iteration, because sometimes it may not converge. Okay, and if it can converge, then within the maximum number of iteration, then it's find the optimal weights. Okay, so that's machine learning's concept. And here's a random state is one that means this training can be repeated, okay, regenerated. And then you first create the model, then you fit the model, then you can predict, okay? And then you can also collect the R square, R2 score, and the mean squared error, okay? So, and we can also see for machine learning model, normally will not give you the p-value, f statistic, t statistics. It doesn't, because those are regarding a statistic, okay, and the confidence level, okay. So the perspective is a little bit different. Okay, so normally for machine learning, what we care about, the performance metric is the accuracy, those are R2 score, mean square, and plus some other performance measure metrics. And next class, we are going to learn those. Okay. And with this model, then let's see, we also do the plotting. Okay, so similar concept. And after we do the plotting, if you take a look at the result, it's not good. This line is not a good line. Okay, so we can see, yeah, if you use the multiple layer perceptron regressor neural network in machine learning is a very important major part, especially right now for all of the deep learning. It's the foundation, but you can see, okay, for the linear regression, in this case, it's not good. So a complicated model doesn't mean it's always good. Okay, so in this case, we can see the scikit-learn that classic packages, libraries, the linear regression model works much better, is it, than this case. Okay. So, and we can also see a lot of time when we do the modeling, you can try use a different approach and then find which one is the best model. Okay, so here you see we try with both statistic and the machine learning model. And next, let's do some other little bit of more discussion. Okay. And so for machine learning, for linear regression model, it's based on the cost function. So cost function, basically the idea is the same. So basically this is y hat and this is a sample data. Okay, but the way to find, so basically this is W0, this is W1, to find the weights, find the best weights. That when you have this model, when you do the prediction, then the result is the best. Okay. So for machine learning, it uses like I previously explained, use gradient descent, okay, to find. So gradient descent involves the learning rate, and you can see it involves a loop, okay. So the idea is to try to find the lowest. So in this case, it's kind of like so basically it's just to try to find the lowest point. Okay, lowest point. So this is X and this is the weights. Okay, you try to find, so you assume, you initialize a weight. You pick some weights and then you gradually use the gradient descent to approach to find this optimum point. And when you reach this point, and then that square of arrow, that's going to be the minimum one. Okay, so that's the idea. And basically, if we project, it's kind of like the topology, then you get to this point. Okay. And that's a completely different topic, okay, regarding gradient descent. So we just get some very, very basic idea, okay. Mm. Oh, so over here, what I'm trying to uh, say is because our example just a single independent variable, okay, but linear regression can be also applied with multiple variables, okay. So then it's just represent like this case. And then next, let's see. Um, And sometimes we can also do polynomial regression. So what this idea is, uh, we use a polynomial, okay? So like over here, this is still a single independent variable, okay? So single, but you have polynomial term, okay? Uh, Basically, polynomial regression, if you do the conversion, then you can convert this like this. You set it as x1, and this you set it as x2, as it like if this you can set it as x3. Then you can convert it to, so from polynomial, you can convert it to linear. Okay, to linear. And then you can apply linear regression, okay, to find the coefficient and then convert it back to the high order term, to the polynomial regression. Okay, so that's the idea about polynomial regression. So basically, we finished the major topic of today. Okay, it's about linear regression, and we can approach it in statistic approach. We can also approach it in machine learning. Okay, and it's from different perspective. So next class we are going to learn the classification. So it's about discrete value. So for linear regression, it's for continuous value prediction. Okay, and next class we're also going to learn how to do clustering. Okay. Okay, so that's all for today. If so, I'm going to end the recording.